Welcome, secondary educators. In this screencast, I'm going to take you through a talk that I gave at the Association of Math Teachers of New York State a few years ago. The main thrust of the talk is the following. Uh, all you need are reflections. That's the whole thing. You have rotations if you have reflections. You have translations if you have reflections. You have everything you need if you have reflections. That's the big point of the talk. Let's remember what reflections do. And let's remember that this is a neutral geometry theorem. So this is true in Euclidean geometry. This is true in hyperbolic geometry. These are the properties that reflections have. There is a reflection in every line called rho sub L. It takes all the points in the plane to all the points in the plane, and it has these 5 properties, and this is discussed in most sections of Math 335, I think. We do cover what reflections do here at SUNY Geneseo. So let's talk about what happens if you reflect over 2 parallel lines, a composition of reflections over 2 parallel lines. So we take triangle AMT, reflect it over L1, reflect that image over L2, we get triangle NYS. Pause for a moment. What single transformation takes triangle AMT and maps it to triangle NYS? Well, it appears that it's a translation, that triangle AMT has translated to this position over here. Can we justify that? Sure we can. The reflection over L1 takes point M, this distance to the line, and then this distance through the line to its image over here. And then this image point goes to the line and through the line of reflection, ends up over here. So what do we have? We have a translation along a vector that is perpendicular to the lines of reflection, and we have that is twice as long as the distance between the parallel lines. There's just as much green outside the parallels as there is inside the parallels. There's just as much red outside the parallels as there is within the parallels. And so the distance we have translated is twice the distance between the parallel lines. So if we have reflections, we have translations, no problem. Well, what happens if the lines are perpendicular? Triangle AMT becomes triangle NYS. How does that happen? What single transformation takes triangle AMT to triangle NYS? Well, I hope you see that that's a half turn about the point of intersection for the reflection lines. Can we justify that? Sure we can. We know that in a reflection, this angle is preserved, and in a reflection, this angle is preserved. And we know that because the lines L1 and L2 are perpendicular, red plus blue is 90 degrees, so 2 reds and 2 blues, that's a straight line. And so we have a half turn centered at the point of intersection of lines L1 and L2. We can accomplish a half turn by reflections. Well, what if the lines aren't perpendicular? Does the same kind of thing happen? Pause for a moment. How does triangle AMT become triangle NYS? Well, it becomes triangle NYS in much the same way. We have the red angles preserved. We have the blue angles preserved. In this case, red plus blue is not necessarily 90 degrees. Red plus blue is whatever this angle is between the between the intersecting lines. And so we have a rotation centered at the point of intersection of L1 and L2. And the angle of rotation is twice the angle between the intersecting lines. So we can do rotations if we have reflections. Rotations are accomplished by reflecting over 2 intersecting lines. So it seems like we've got a lot going on. And that's all the isometries, right? You got reflection, you got translation, you got rotation. That's all there is, except that it isn't. Well, how do you do that? How do you do a glide reflection? Well, a glide reflection is a reflection and then a translation, right? And a translation is reflections over two parallel lines. So it gives us a chance to think about, well, three lines. Three lines. And it turns out that every isometry in the plane is the result of no more than three reflections. Everything we could imagine doing in the plane, we can do with no more than three reflections. So it bodes well for us if we consider in how many ways can three lines fall. Well, three lines can fall where they all come together at a single point. And if they all come together at a single point, is there a single transformation that maps triangle AMT to triangle NYS? Is there such a transformation? Well, the answer is yes. It happens to be a single reflection. If you have reflections over three lines that meet at a single point, a single reflection in this red line does the job. Where is that red line? Well, we measure whatever the angle is between the first two lines of reflection, and then we back construct that angle from the third reflection line. And it turns out that this red line, where this angle is the same as that angle, this red line is the single line of reflection that turns triangle AMT into triangle NYS. It has to be a reflection, a single reflection, because orientation is not preserved, and reflection is the transformation that reverses orientation. Well, what if the lines are parallel? What if it's this case? We reflect over this line and then this line and then that line, right? We go over 1, 2, 3 parallel lines. Well, what does that? Well, AMT becomes NYS. It has to be a single reflection. Orientation is not preserved. Where's that line? There's that line. Where does the red line come from? Well, whatever this distance is, we back that up from the third reflection line, and it turns out that this line, made by making this distance the same as that one, this red line is the single reflection line that turns AMT into NYS. That's fascinating to me. Fascinating. You can do three things with one thing. That's crazy. Well, what if two of the lines cross? What if it's this scenario? So we reflect over, I don't even, that's just, it appears that we've reflected over N and then M and then L. It appears that this is N, then M, then L. It is not obvious what transformation takes AMT to NYS. We're pretty sure there's got to be a reflection involved. Glide reflection also does the job. It turns out that glide reflection does do this job. And here's how we know. So we do reflect in N, then reflect in M. That's some angle of rotation. There's an angle between N and M. Well, no matter where you put N and M, as long as they go through this point and they have this angle between them, we're gonna get a rotation of 2 theta centered at point P. So it doesn't matter if we make that angle here between S and T, or here between N and M. The single transformation accomplished by these two intersecting lines passing through P is the same as the single transformation accomplished by these two intersecting lines intersecting at P. But the advantage of line S is that it's perpendicular to our third rotation line. To our third reflection line. Line S is perpendicular to line L, and that's an advantage for reasons we will see soon enough. So we just swap out lines N and M for lines S and T. That's pretty slick. But it's still not obvious what that does until we realize that these lines are perpendicular, and so S and L will give us a half turn centered at Q. Well, any two perpendicular lines that intersect at Q will do the same thing that S and L do. So these two lines that are perpendicular and intersect at Q will do the same half turn that S and L did. So we can swap out these two lines for S and L. And now we have three lines of reflection that do the same things that the other three lines did, except looky there. It's a reflection and a translation. What takes AMT to NYS? It's a glide reflection, which is so not obvious from LM and N from 3-4 slides ago, right? It's so not obvious. But in this slide, it's really obvious. And we proved along the way that these three lines will do what the other three lines did. So we just make the swap. Why are glide reflections a thing? Glide reflections are a thing because of algebra. Algebraists love groups. So what's a group? The set of isometries, and here are all the isometries, right? You got the thing that does nothing, you got the reflection, you got the rotation, the translation, the glide reflection. Why does glide reflection have to be a thing? Because the set of isometries with glide reflection in it is a group under composition. What's a group? It means that there is an identity, there's something that does nothing. There's invertibility, everything that's done can be undone. There's associativity, and that's, you remember, and there's closure. Closure. If we do reflection and translation, that composition has to be in the group. Otherwise, it's not a group. And that's the only reason that glide reflection is a thing. But the upside for us is that there will never, ever, 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 ever be some new isometry that somebody discovers on some campus somewhere and shares with the world. We have proven that there cannot be another isometry that isn't one of the ones we have already described. We have them all. And that's somewhat comforting to know. So reflections are all you need. They do everything you need them to do. We can put them together in creative ways to get all the results we want. And that's comforting. All right, I will look forward to seeing you when we gather.